I just have one question for you. Do you know what time it is?
Well, it's 6:15 p.m. Let's get to work here. This is the Geometry Final Fall Exam video review, and I am super stoked for this. I have no idea why, because I'm going to be talking for like 2+ hours, so we're about to get to work here. This is what's going to be covered sequentially, all these problems starting from 42 through 45 on page 41 and going through there. I won't know which units what. Well, I mean, I should, but most problems will be diverse enough, and if you ever have any trouble and you want to just find a specific problem, go to the description section. It's somewhere down below here. I'm sure it is. I'm pretty sure, even on an iPhone. But if you're on a computer, down below there, try and find the timestamp for the one problem that you're looking for. You'll be good to go. All right, let's do this thing. Numbers 42 through 45 all are based on the same exact figure. We're going to solve for x with each of these, and I'm going to be doing each one down below like this, so you're going to have to pay close attention to which problem. So here, I'll just write 42 right now. I'll have to get in the habit of this. Okay, so what we're going to do is use the idea for all of these. It just depends on what you're given. That if I add any two angles together, like this one and this one, then it's equal to the entire angle right here, which is actually what it probably looks like the first one's all about. And also these marks here indicate that these two angles are congruent. So we'll go from there. We'll set up some equations and do some work. Number 42, the measure of angle AOC, which is this big guy right here, well, not big, but two angles, is 7x minus 2. AOB is 2x plus 8. Okay, I'll do that and that. And then BOC is 3x plus 14. Okay, so the idea, if I add AOB with BOC, I'm going to get all of AOC. So that's the equation that I'm going to set up, and these expressions help us figure that out. Then after that, we have to find the angle measures. That's a part of it. Sometimes I may end up skipping that. We'll see. But if I add AOB with BOC, I get AOC. So 2x plus 8 plus 3x plus 14 is equal to 7x minus 2. Hello. So that's the beginning part there. And again, that's called the angle addition postulate. Adding two angles with a common side and common vertex give you the full angle measure there. Combine like terms, we get 5x plus 22 equals 7x minus 2. Subtract 5x from both sides and add 2 to both sides, you get 2x equals 24. Divide both sides by 2, you'll get x equals 12. From there, you can substitute 12 in for all of these angle measures. There are different ways you could go about it. Once you have two of them, like I get AOB here, that would be 2 times 12 plus 8, so that'll be 32. Okay, BOC equals 3 times 12, which is 36, plus 14, which is 50. So AOC, it is the sum of both of these, so you could either substitute 12 into here, which would give you 84 minus 2, which is 82, or it should be 32 plus 50. So that also seems to work as well. Perfect. So there's the first one. Once you start adding those up and solve for x, you're pretty good to go. That's number 42. Number 43. The measure of angle AOB is 4x minus 2. So let's see, that's this guy right here. Yep. BOC is 5x plus 10. And then COD is 2x plus 14. All right, so how to begin this problem? Do we add all of these and make it equal one angle measure? Problem is, you don't know what the entire thing, what AOD is. So it's not quite like that, but rather, you do know that AOB and COD are congruent to each other because you see tick marks here and here that indicate that these two are the same thing. So what you can do is make an equation where those two are equal, and once you solve for x, you can find each angle measure. So what I'm going to do is say, measure of angle AOB, 4x minus 2, is equal to the measure of angle COD, 2x plus 14. Subtract 2x, add 2, divide by 2, you'll get x equals 8. So again, this angle measure is equal to this one right here. The tick marks say so. That's kind of the help we get from that. So once you substitute 8 into either equation, you can get measure of angle AOB and BOC. I'm sorry, COD. And that is 8 times 4, which is 32, minus 2, which is 30. So you should be getting 30 for either one, and I should be leaving units. That's degrees. BOC, don't forget that one, is 5x plus 10, so 5 times 8 is 40, plus 10 is 50. And there you are. That is number 43. How are we on time? We're good. Number 44, as I erase all that. Okay, number 44, the measure of angle AOB is 28. It's good to have an actual measure every so often. BOC is 3x minus 2. Okay. And AOD is 6x. Entire thing. Okay, in this case, once again, it's kind of a matter of if we add this AOB plus BOC, we'll get AOC. But we're missing COD to add to get AOD. But aren't AOC and COD congruent to each other? Oh yeah. These two are equal. So if only I double the number 28, I'll get 56 for the two of these combined. BOC, hanging out in the middle, is 3x minus 2. So 28 times 2, which as I said would be 56, we'll get there, plus 3x minus 2 equals all of AOD, which is 6x. So 56 plus 3x minus 2 equals 6x. 56 minus 2 is 54. I subtract 3x from both sides, I'll get 3x on that side. And we'll get x equals 18, if I'm doing my math right there. Okay, you solve for x. Now you have to find the measure of these specific angles that they're asking us for, which is technically kind of all of them. Measure of angle AOB is the same thing as the measure of angle COD, but they're not asking us for that one. But that one's 28. I guess we already knew that one. Measure of angle BOC is 18 times 3, which is 54, minus 2, which is 52. And then the measure of angle AOD, you could either do 6 times 18, or you could do 28 plus 52, which that should give you 108 either way. And that is number 44. So going on to 45 now. Last one here, we have measure of angle AOB is 4x plus 3. Measure of angle BOC is 7x. Measure of angle AOD is 16x minus 1. So it's the same thing as the last problem. The only difference are the expressions. Otherwise this is the same kind of problem, except now there are more expressions, different expressions. Now we have to, if we want to multiply, if we want AOB and COD to be the same thing, we'll have to double this amount. So just like last time, we'll double that measure. Then we're going to add 7x, the BOC angle measure. And that'll equal all of AOD, which is 16x minus 1. So saving you some math here, 8x plus 7x is 15x. Subtract 15x from both sides, you'll get x on the right. Add 1 on this side, you'll get 7 on the left. So x equals 7. So the measure of angle AOB, I'll just write it up here. 7 times 4 is 28. 28 plus 3 is 31. BOC is 7 times 7, which is 49. These are degrees. And AOD is 7 times 16. Oh, that's 112. Minus 1 is 111. To double check, if I double 31, I get 62. 62 plus 49 is also 111. So we're good. So those are angle measures. Again, that's using what's called the angle addition postulate. In case we don't run into it, which I don't think we are going to, there's also something called the segment addition postulate, which means if you add two segments joined at the same endpoint and they are collinear, you get the length of the entire thing. So this segment plus this segment, if those were collinear, equals the entire thing. That drawing was, for example. Okay, moving on. Number 9, we have ray GH that bisects angle FGI. We want to first solve for x and then find each angle measure that's being asked for. So an angle bisector is something that is drawn literally right in the middle of this entire angle, which means when it's split apart into two different angles, the angles are congruent, which is actually what these markings mean. So this angle, FGH, is congruent to angle HGI, which also means the measures of their angles are equal. So 3x minus 3 is equal to 4x minus 14. Subtract 3x from both sides and add 14 to both sides. You'll get x equals 11. Okay. Find the measure of angle H. Let's see. Measure of angle FGH. So this little thing, that's 3 times 11 minus 3, which is 30 degrees. I'm trying to save time any way I can. Measure of angle HGI should also be 30 degrees. If you want to double check that here, 11 times 4 is 44. 44 minus 14 is 30. Measure of angle FGI, the entire thing, is 30 times 2. You double them. You add both of them together, and they're the same thing. That's number 9. I'm just going to move on, if that's good enough there. Once again, that's an angle bisector. Okay, find the distance between the points to the nearest tenth. We have points C and D right here. And actually, I didn't draw any graphs for myself, so I'm really gonna rough this thing. So I want you to kind of bear with me, and I'm gonna do the best I can to help y'all out. But what I want are these 2 points, and there are different ways that you can do this. You can use distance formula, which is what I'm gonna use last, because I really want you to think about what it is that's happening here. But it's also a counting measure, and I'm going to talk about that next, actually. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I have to go all the way up to 18. Oh, this is going to be fun. See, sometimes graphing it ain't exactly just as good, but I need to use this as an example. Okay, so I have 2 points, 12, 6 right here. This is C. And then I have point D, which is at negative 8, positive 18, way up here. Okay, and I need to find the distance between the two. So, what this is a right triangle, if you draw it the correct way. And none of my drawing stuff's perfect, that's not the point. The point is figuring out what distances you are actually calculating. What I need to do is I need to find out how much I'm rising and how much I'm running. And in this case, the rise, if you call rise this way, you can also say this is fall. And running, if I say run, I should probably mean in the positive direction. How much did things change? How much did I change going from negative 8 to 12? How much of a jump is that? You could count it, 1, 2, 3, 4, etc. Or you might practice your math enough, you know that any distances you have to subtract. Or to find the distance of something, you have to subtract one from the other. That'll give you 20. 12 plus 8. You get 8 to go here, the other 12 to go here. That's 20. From there, you have to consider how much this thing fell from 18 to 6. Okay, that's 18 minus 6, which is 12. Okay. This here, I don't want to call it C or D because we already have those. I'll just go ahead and can't call it X or Y. Let's call it Z. But if you think about this, really, this is a right triangle, okay? And we have the legs of the right triangle. We have the hypotenuse that we need to find. So what I'm doing, really, is I'm setting a Pythagorean theorem. Z squared equals 12 squared plus 20 squared. So that's 144 plus 400, which is 544. Now, they did ask you to round to the nearest tenth, so what you'll do in your handy-dandy calculator here is make sure it's set to classic so you can actually get a decimal reading. Square root of 544 rounds out to 23.3 units. Okay, not a very perfect number there, but there you go, that's the length from one to the next. Now, how did I do this? Again, I used Pythagorean theorem when I graphed this, which I didn't have to. I just wanted you to see the right triangle that's involved. You're trying to see the distance between your x values. This is also known as x2 minus x1. and the distance between your y values, also known as y2 minus y1. You can see my calculations up here, x2 minus x1, y2 minus y1. And notice that the sign didn't matter. Like, this really would have been a negative 12, but I'm going to square that number anyway. Right, so which one should have I actually done? I probably should have done 6 minus 18 because I did 12 minus negative 8. Anyway, that's not really the point that's involved here. What matters is that you understand that distance formula is, if I took the square root of this and this, z would be the square root of x2 minus x1 squared plus y2 minus y1 squared. Both of those together. So that's what the distance formula looks like. Okay. Nothing to try and memorize here. If you know it, you know it. If you don't, find an alternative method, period. I mean, just period. Just don't try something else. And you can just draw it, too, if you want to count. If you want to do your tick marks and stuff, they don't have to be perfect. Just do the best you can. Okay, find the midpoint of hx when you have, I don't like those points. Okay, I don't know if I really want to calculate oh boy, yeah, you know what? I don't know if I want to count this one this time. This time maybe it is good to do midpoint just by actually doing the midpoint formula, which I'll look at in a moment. I still want you to see what's happening here, what midpoint really means. I mean, I do use midpoint formula, but I don't see it as a formula. I see it as the average of 2 points. And really, that is what we're looking at here. So let's go ahead and plot these points here. I have negative 6.3 comma 5.2. Yeah, that's h. And then x is 1.8 comma negative 1. Beautiful. And I need to find the point that resides right in between these two. Okay, and here we go. Boom, boom, boom. So I need to find out where's that middle guy. And, sometimes it's actually, you can count it, you can do stuff like that. This is a little bit different because now your values are so decimally. You still could, theoretically. We're doing the same kind of thing. We're not finding the distance. You could, but counting it this way isn't really going to help anybody anywhere. So what's going to happen is if you figure out how much it does run and rise, you could have that distance and you can go that way with it. But that would, in this case for me, I think that really would require a graph. So going from 5.2 to negative 1, that's going down 6.2. And going from 1.8 to 6.3, that's 8.1 across this way. So if you were to have those values, which is not very fun, especially for 8.1 here, half of that is 4.05. So unless I did math wrong, because I'm doing this in my head here, and half of negative 6.2 over 2 is negative 3.1. So the idea is that you can use these values here, and you can take them from, excuse me, depending on which side you're looking at. If I'm looking at h, I'm going to go from negative 6.3, and I'm going to go over 4.05 to the right. Okay. And I'm going to go from 5.2 and I'm going to go down 3.1. If I went from x, I'd be doing the other way. I'd subtract 4.05 and I'd add 3.1. So this gives me, oh boy, negative 2.25, which is negative 2 1/4. And this gives you here 2.1, which is 2 1/10. Let's confirm that my answers were right because there's no guarantee that they were. The other way that you would do it is kind of through midpoint formula, and I'm going to explain what the formula is, not just writing it out for writing it out's sake. Again, not something to memorize, it's just something to understand. If you're going to find the midpoint of two things, you have to take the average of them. The average of your x's, average of your y's. So, take the average of my x value, and that'll give you the exact location, by the way. What I had to do in this example was I took half the distance. Half this distance, half this distance. That got me to this point over here. Which, hey, that's not bad. Negative 2.25, positive 2.1. So it makes sense, right? Where should your midpoint be in the second quadrant? I'm looking for that kind of answer. So you kind of know where your thing should be at if you do graph it. That's kind of the good thing about it. So I have to take the average of my x values, the average of my y values. Okay. Now notice here, I'm adding, even if the things are negative, and then you do what you need to there. This becomes negative, oh boy, negative 4.5, which it looks like that does give you negative 2.25. Then 4.2, which looks like it will give me 2.1. These things do point back up to here. This gives you the same result over there as that midpoint. As that midpoint right there. So there's your midpoint. Not very pretty numbers, but the midpoint stuff still applies. Either do one of these deals here, or you use midpoint formula and go about it that way. That's number 22. Okay, number x squared. Oh, number 6, find the value of x. Okay, this is back to Pythagorean theorem. I'm not really sure why the problem was requested, but one thing that I do want to talk about as far as what people might accidentally do. Now, don't do this, okay? I'll write this out in red to say no. 15 squared plus 17 squared equals x squared is not the correct way to go about this. I think sometimes what people think is that your variable is the one that goes by itself. Not necessarily true. What happens is you have two legs. Jeez, perfect. You have two legs and you have a hypotenuse. And hypotenuse is always the longest side. It's opposite the biggest angle, for one thing. And for another thing, it's these two legs meet at the hypotenuse. I mean, I don't know. There's really no other way to explain it. But this is your longest side, and hypotenuse is the one that goes in at the end. If you do a squared plus b squared equals c squared, a and b are your legs, and c is your hypotenuse. So we're going to do x squared plus 15 squared equals 17 squared. Now next semester we're going to learn some things called Pythagorean called some special triangles, some special Pythagorean triples. This happens to be one of them, which is called an 8, 15, 17 special triangle. So knowing ahead of time your answer is going to be 8 is always a good thing that I'm telling you right now. Now by the way, the answer to the square root of x squared equals 64 is really x squared equals plus or minus 8. But distance can't be negative, so we ignore the negative portion. It's just the positive version, positive 8. An extraneous solution, that one is. Okay, so 8 is your answer there. Find the values of the variable. So obviously we're switching gears here. This is a new chapter. This one's involved in chapter 3, okay, or unit 2 if you're in my class looking at this stuff. I do believe this was also on a quiz. So there are a lot of ways I can talk about this problem. For the sake of time, I might shorten that a little bit and not say I'm going to talk about all ways here. But one thing you'll do is you'll say, which things can I figure out first? Because there are sometimes when you can't figure out some things before others. For example, it looks like it'd be hard to figure out angle y here because it's involved in both of these right here. It would only work if I knew one of the other ones. Okay, some things you cannot assume. I cannot assume that these are 90-degree angles over here, unless I do a little more work to figure out that they are. So no assumptions there. I can assume these are congruent, and actually I think someone in one of my classes actually worked for that, figured out these were congruent and did something with it, made it work. But what I'm going to really dig into are the parallel lines. So these blue lines are marked parallel, yes? And to make this really stand out, I'm actually going to make them a little bit bolder for y'all. I'm going to make these, big and blue. Okay, you can't see anything else there other than other angle measures, but I don't really want you to look at any other black lines. Now the question is, which angles are formed using these lines and then another set of lines? Well, I'm going to drop you a little something here. There are 4 different transversals I could use and do angles with. I could use, let me do a bigger blue there. I could use this line and call it a transversal, where now if you just look at the blue lines, take a look at this. Here's an angle. Here's an angle. They are same side interior angles that are supplementary because these two lines are parallel. Let me actually emphasize that a little bit more. This line is parallel to this line right here. That makes these same side interior angles supplementary. The problem with that statement is it says x plus y plus w plus 42 equals 180. Well, that's not going to help me solve for any triangle just yet, or any angle just yet, because I don't quite have any variables yet. So starting with this angle might not be the good one to do, or with that as a transversal. So let's go ahead and say we could use this as a transversal. Of course we could. And when we do that, which angles are formed? These two angles here, which are alternate interior angles that are congruent, which means y equals y. Well, I think we know that, and unfortunately that doesn't really do much help for us, doesn't help us solve for y. So can't quite use that one just yet. We might later, well, I guess we won't, because once you find out y, you find out y. So that one's not going to be of much help with those two lines there. It might for other ones. There's this transversal right here for these two lines, which gives you these two angles right here, alternate interior angles, W and 25. That one actually works for something. It actually tells us that W and 25 are the same thing. So what can I do for this previous statement right here? I could actually substitute 25 in for W, and I'm actually starting to make some progress here. So I can use that. That actually helped me out. But not yet done. I still have to figure out some more angles to go along here. Okay, and then I also have a final transversal here with these two parallel lines that gives you V plus 25 plus y plus 76, which equals 180. Because again, these are same side interior angles, and the angle addition postulate says V plus 25 is that entire angle. So once again, not something I can fully flesh out just yet. There are some other things I probably could have done with that, but let's leave those be for now. You got some work taken care of. Let me actually even replace that W there with 25, because now we know it's 25. Now, you don't have the special technology of colors and thick pens and stuff and erasing like I do here on your paper, but please do the best you can. And I'm just giving you the perception opportunities here. I want you to kind of do the rest and say you don't technically have to do all this big, bold stuff. I'm really just giving you what it is that we're looking at to help you. Okay, these two lines are now marked to be parallel here. So let's go ahead and say, oh, this is parallel to this here. Now let's make some transversals out of it. There are 4 different ones we can do, starting with this one down here. And I could make the statement that x plus y plus v plus 25 equals 180. Okay. Now, you could actually do some stuff with this, it looks like. So take a look at these two statements I made last time. Okay. I could actually look what they have in common. They have v plus 25 and a y, actually. V plus 25 and a y, so plus y. If I move that all on the other side of the equation, on one side I have 76 equals 180 minus v plus y plus 25. On the other equation here, if I subtract everything, I have x equals 180 minus v plus y plus 25. There's a little something called the equal values method here. If 180 minus v plus y plus 25 equals both 76 and x, that must mean that x equals 76. Pretty interesting. Do you think we can use that? Let's check and see if doing some more work in here will actually give us 76 for x. But that's actually just a way that I could have gone about this problem. Didn't have to. Felt like it to say, hey, that's something you could do if you really wanted to. I'm sure there's an easier way, though. Let's keep looking. Let's do a different set of lines here. Instead of that, let's check out dividing these two here. And now you're looking at alternate interior angles that are congruent because the lines are parallel. That make what two things congruent? It make 76, this angle formed here, and x. Look, x and 76. They are. It looks like they are the same. I could have just gone over there and done that work. Yes, you could have. But I tried to show you just a different way. There's a lot of ways you can rewrite these things. Now here x becomes 76. Now it looks like I could actually solve for y, because all this stuff is now separated in such a way where y is all by itself. All these values are different. Okay, so let's see. We're going to get 25 plus 42, which is 67. 67 plus 76 is 143, I think. So 143 plus y equals 180. Whoa, subtract to get y equals 37. Okay, so there's 37 now. Let's not get carried away here and say that that's the only way to get y. I'm sure there are other ways. Actually, they might be a little more difficult. Let's see if we can use this y in for this later to figure out what v is, because it looks like v was actually a pretty simple one to solve here. If I just move this guy over here Looks like I have alternate interior angles V and 42, which means V would equal 42. Let's double check and see that we get that over here. If I substitute 37 for Y in this equation, I'm going to get V plus 25 plus 37, that's Y, plus 76 equals 180. I know, this is a messy problem, I'm sorry. I'm giving you all these different ways. 25 plus 37 is 62. 62 plus 76 is 138. And subtracting, yeah, it looks like we get V equals 42. So it looks like we're in some good business there, and we can do it that way. Now, how else could have we gotten Y? Really, it's just about what different things you could have added to get Y. Otherwise, I mean, look, Y is going to be the hardest one to achieve. You're going to have to find different, like this setup here. If I move this over here, we could have set it up saying 42 plus 25 plus Y plus 76 equals 180. Oh, look, look, that's right there. Oh, look, it's a parallelogram, so you're going to have opposite angles that are congruent here. So this, it looks like this would have been the best setup for us. But we still have 42 plus 25 plus Y plus 76 equals 180, just like we did. So again, Y would have been the most difficult one, but we get V. Let's see, what order is this? T, U, V, W, X, Y, Z. V, W, X, and Y. So we got all four. A lot of different ways to go about it, but again, the original problem, if I really were to just, clear everything, okay, you got to do your best to try and find where those lines are. If lines are parallel, like these sets, make a transversal. Okay, if you have to use your pencil and do some, erasing and like whatever, do that. But that's really the best way to go about it. That's how you're going to find things. If you can recognize W and 25 are alternate interior angles, especially after doing so many congruent triangles, triangles being proven congruent, or Y and Y, X and 76, V and 42. Technically, 3 of them are found using alternate interior angles. Y, the last one, is found doing some extra stuff. You have to add a couple things up to get 180 degrees. There are a lot of different ways you could have done it. That's number 24. Okay, number 25 with the same thing. It's that same kind of issue. You get L is parallel to M. So it's all about these two lines cut by different transversals. And once you really, the key is once you find the transversals, then you're really just trying to determine where angles are formed. Okay, so if I make these two lines kind of more prominent there are two different transversals. There's this one, which forms which angles here? Looks like technically none. Even this 5x, this angle is not being formed here. This angle is being formed there. So doesn't look like this transversal is helping me very much. So I'm going to kind of ignore that one for now. Let's look at this transversal here. Okay, now it doesn't, once again, this 5x is only this. 5x isn't the entire thing. But what I do have is this angle, and I have this angle. Now, strangely enough, these angles do not have a relationship with one another, such as they are not corresponding, they're not alternate interior or exterior, not same side, nothing like that. But what you can do is you can start to get a look and say, well, here's a corresponding angle right here that would make, I should make these different marks, that would make this 2x as well. So you can do something like that and say this is a linear pair and they add up to 180. That's really the way that this setup is going to be made. What else you could do, actually, though, is you could say 5x plus 40 is also over here because they're vertical angles. And because of that, boom, you have same side interior angles with parallel lines. Those also add up to 180 degrees. So you can solve for x this way, and I think that's the plan for this problem. And you're going to get x equals 20. Okay. Now, I don't know if this was a decoy. I mean, I guess it was, but I don't really know what else they'd be asking you to go for with it. I don't know anything about this line whatsoever, and they're not asking you to find the angle measures either. But if you wanted to know what this angle measure was, well, it's going to be 100, because 5 times 20 gives you that. So again, it's kind of a decoy, just like this line was. Was this line ever used? No. Was 5x ever used here? No. Not in this case. I'm sure there were other ways you could have figured it out. For instance, if this is 5x plus 40, actually, you know what? Here's how you could have used it. If this is 5x plus 40 here, these over here, green and green, these are alternate exterior angles. And if this is 5x right here, then this right here is 40 degrees. Now you could have used something there and done this whole thing as 5x plus 40. You know, it could have been used. I don't know how much you would have used it, but, oh, you know how you could have used that? Check this out. This is 40 degrees. Vertical angles, this is 40 degrees. And well, I guess there's no way of you knowing that this is 2x equals 40, that these are the same thing. Anyway, I'm just, spewing a little bit of nothing here. But these are ways you want to work around the problems. I think that's the point I'm trying to say. I'm trying to reinvent this problem as I see it. So really, that's all you're going for. Okay, here on number 6, I recall seeing this problem on some of the homework stuff. This was one of the tougher problems when early on you were still trying to get your, groove in with those parallel lines. So let's take a look at this one with the same kind of way. You have your parallel lines right here. Okay. Now the question is, where are your transversals? Here's one. Okay. Now, as you see this transversal, you say, all right, well, here's an angle that's formed, et cetera, et cetera. Looks like we have a bunch of right angles, right? Parallel lines. This is part of chapter 3. Parallel lines. If this is a right angle, then so is that, because they're corresponding angles and alternate interior, all this kind of stuff. They're all right angles. But it doesn't look like that's really going to help as a transversal. Neither would this one right here. You're kind of running in the same issue. Because this angle formed means nothing with regard to my parallel lines, because this line means nothing for it, unless I use that as a transversal. So what I'm going to do instead is take a look at this one. And so again, it's up to you to really try and make your perception out of this. I know I'm doing this with smartboard tools. I understand that, but it's your chance to try and do this as well. So the question is, how much will this 30 mean for anything with regard to the angles? It won't that much. You're going to have to be very, very cautious about the fact that this 30 means very little unless you want to refer to 30 plus this right angle right here, which is a little different. And these are not vertical angles, mind you. This is not 30 right here. It's not kind of how it works. Instead, I would really look at the fact that if this is 30 and this is a right triangle, well, 30, I shouldn't give away the answer yet. Let's call this x. 30 plus x equals 90. Again, here's your right triangle. Choose a different color. Here's your right triangle. One of the angles is 90 degrees. If they all add up to 180, subtract 90, then these two add up to 90. Okay. In a right triangle, your other two angles are complementary. So x is 60. Now, how does 60 help? Well, we're trying to solve for c. Remember, work at what you're trying to solve for here. And if you can see here, these are corresponding angles that are congruent. Again, only look at the blue. Well, if I call this blue. Only look at the blue. 60, 60, parallel lines. Corresponding angles are congruent. C equals 60 degrees. Okay. So that's the aim for that one. I think we're good to go. That's number 6. Number 26. All right. Here we have a big right triangle. Within there, you have this line, which now divides a couple different triangles here. So we have to solve for a through e. Okay. So I'm already going to write a equals b equals etc. on my way. Question isn't the question is which one do we solve for, but it's not a matter of always solving for a first just because it's the first letter. I'm sure there's a way that you probably could, but which letter can we solve for first? E. Looks like E is a pretty good one here. E is going to be 90 degrees because it's an exterior angle and it's also supplementary. Get out of my way. Postpone. A day. Get out of here. I'm doing a video. Can't you see? God, the nerve of some things. E is 90 degrees here. Okay. So pretty simple to figure out there. I think B is kind of the next one to do because this is 32 degrees right here. And B and 32 are complementary to each other. You can tell because these both add to 90. So B is 90 minus 32, which is equal to 58. So B is 58 degrees. Once you do this and you've drawn this diagram, because if you're doing this as like homework, then clearly you've drawn the diagrams. Scrap that out and put in the 58. That'll be good for you. Now I can work toward A, it seems, here. And you can get 55 plus 58 plus A equals 180 degrees. And so that'll be 113. So A equals 67. So we're on our way here. We can solve for D and C. Actually, you know, you could have solved for C in the very beginning as well. There were 3 different things you could have solved for in the beginning, actually. It's just, you know, you want to say different ways to go about this problem? Oh, I could spend a long time doing different ways about this problem. I could even talk about the fact that D plus A will give you E over here. That's how I could solve for D. But anyway, so here we have D plus 67 equals 90 degrees. Again, the reason is because in a right triangle, one of your angles is already 90, and if all of them add up to 180, take this 90 out, these two just add up to 90. So D equals 23. I'm just saving you a step and extra calculations where you might mess up. I think I'm supposed to write these over here. 23, 67. C, the last one, and probably maybe the easiest one. Well, E, I'd say E was the easiest, but C and 55 here are supplementary. So 180 minus 55 will give us C, which is going to be 125 degrees. I really should get in a habit of leaving units here with degrees. And there you are. Talking about other ways we could have gone about it. If you solve C first by getting that 125, then you can add these 3 up to get 180. So stuff like that could have gone, and then you could have gone very special in terms of setting 2 equations equal to each other using equal values method. But I'm done with the problem. I'm moving on. All right, this is still in chapter 3. Find the measures of the interior angle and exterior angle of each regular polygon. Here I have a 100 gon. Now, if I go to my tools here, and if I expand this and I find, hey, where's my 100? Honestly, it doesn't matter. Honestly, a 100 gon might look a little bit like this, because you probably wouldn't even see the sides very well. It might just look a whole bunch like a circle. As you can tell, the 16 gon, let me go back to that. The 16 gon already is kind of getting that circular look, but you know, you multiply these by 2, meaning you get extra, you know, you cut these in even more halves, and then multiply by 2 again, you're getting really close to them. But we don't need to draw it. The idea behind this, though, is a few things. First of all, for any n-gon, the sum of the measures of your interior angles D is equal to 180 times the number of triangles in your polygon that are made up using your interior angles. And your triangles is made up by doing your number of sides and subtracting 2. So if you want to go straight by formula, we do D for a 100 gon. D equals 180 times 100 minus 2, which is 180 times 98, which I'm not going to use the calculator, and here's how I'm going to do it. I'm going to do 180 times 100 minus 180 times 2. So 18000 minus 360. Haha! I don't even want to do this calculation. This will be 17640. I do believe that's it. Now I want to use the calculator to double check. I don't want to be wrong for you guys. So 180 times 98. Yay, 17640. So now, what did I solve for? This was the interior angle sum. I did not answer this question yet, not even close. In fact, I'm doing it the harder way first, just so you know. There's actually, I'd say there's a much easier way to do this. Now, let me talk about this for one more second here in terms of how formula is derived. Think of a triangle. Okay, a triangle's interior angle sum is 180 degrees. I did not spend time proving it in this video. I will not. A quadrilateral is made up of 2 triangles, if you think about it. 2 triangles, I made a 4-sided shape right there. Here are your 2 triangles. Now, when I say made up of 2 triangles, what I mean is that I am making the triangles out of the interior angles of the quadrilateral, meaning I'm drawing it from a diagonal to another diagonal. So, meaning I'm drawing the diagonal. I'm drawing it from one vertex to another vertex. So here's an angle, 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 here's an angle of the triangle. These are also the interior angles of the quadrilateral. So the interior angles of the triangles are 180. When I add them, I get the interior angles of the quadrilateral. If I added another triangle within here, really, I just made a pentagon. And by that I mean the interior angles of the pentagon are made by the interior angles of the triangle. That's another 180. Each time you're adding another triangle, you're adding another side, and you're adding another 180 degrees. If I wanted to do it kind of a better way, if I did a 7-sided shape, how many triangles are made by the interior angles in a 7-sided shape? Well, you can take a guess and say it would be 180 minus 2, or sorry, it'd be n minus 2, 7 minus 2, and you'd be correct. It'd be 5. How so? 1, 2, 3, 4, 5. And I have to draw it specifically like this because what if I do something like, well, I mean, like I could do like this, for instance. That's still 1, 2, 3, 4, 5. But what if I do something like this? Okay, the problem is the triangles that are now being made. Now, this isn't a triangle. This is actually a quadrilateral. This is 360. This is another 1, 2, 3, 4. This is 360. Actually, I've just made a bunch of quadrilaterals. And 180. How come this isn't the same thing, you might ask? Well, these are not made from is this made from an interior angle in my polygon? No. This is, etc. This is not. So I can't go about it that way. I have to go from only interior angles. So, looking back at this again, I can connect it different ways that I'd like to. I could do something like that and that as I just did last time. But they all have to be made from interior angles. So I make the triangles angles from interior angles of your, in this case, a heptagon. So it's 180 times 5. Now again, where is that all coming from? 180 times 7 minus 2. The number of triangles in a heptagon is 5. So again, that's kind of where it's derived from. I want you to know that. Now, I still didn't answer the question. I have this 17640. What does that give me? I can't even write 17640. That's D, that's the interior angle sum. I want to find the measure of one interior angle. Now, the key word for this thing is going to be regular polygon. So regular polygon means all sides and all angles congruent. This that I drew was not a regular pentagon. This that I made was a regular heptagon. All sides and angles congruent. Now, all sides doesn't really matter here. The angles do, though. If there are 100 sides in my polygon, that means there are 100 angles. If there are 100 angles, I divide by the number of sides, and I will get the measure of one interior angle. Please don't pull out your calculator for this one. Move that decimal 2 places over. You'll get 176.4 degrees for each interior angle. Now, I want you to think about that for a second, because 176 is really close to 180, which means each angle is really close to making a straight line, which is why it would be very tough for you to look at this thing not as a circle, right? It would look really close to a circle. 176.4 probably looks like that. Your angles will barely be noticed. Okay, now that's the interior angle. How do we get the exterior angle? Because we need the measure of one exterior angle here. Well, an exterior angle is made from an interior angle where you extend one of your sides. So if this is an interior angle right here, this is an exterior angle. So it's the supplement of your interior angle. So your exterior angle is 180 minus 176.4, which is 3.6, I think. So there you go, 3.6 and 176.4. Okay, now I did this the hard way. You might ask why I did it the hard way. Because you need to know how to do some things. And sometimes you don't know which way is the hard way. It's just all about practice. But what's the easy way, I guess, is your real question. Well, exterior angle sum, I'll call it E sum, is 360. It doesn't matter if it's a triangle or a 100-sided shape. It doesn't matter if it is regular or scalene. The sum of your exterior angles is always 360. Why? Well, I want you to take a look. When I increase my number of sides, I'm really decreasing what each exterior angle is. Remember what that 16-sided shape looked like? Let me bring it back up again. The interior angles get larger. What happens to the exterior angles? Ooh, they get pretty small here. There are more of them. That's why the interior angles sum gets a lot larger. The angles are larger and there are more angles. exterior angles, they get really acute. They get really small. Anyway, so the exterior angle sum of any shape is always 360. So what's an exterior angle measure of just one of them? You're going to divide by the number of sides. Don't use the calculator. That's 3.6. So you just do your exterior angle sum, 360, always, divided by 100. That gets you one exterior angle measure. The interior angle measure, then, you can just do 180 minus 3.6, which is 176.4. And you can do it that way. A lot easier, but this is still important to know. That's why I went about it that way first, so you didn't just move along. Now we're going to move along. Number 12, write an equation for the line parallel to this line that contains point C. Here's your point C. They should have just said that contains the point 03 that passes through this point. What I'm going to do is I'm going to make some axes here, and the reason why I'm not using pre-drawn axes is because I'm not trusting the fact that you have those as well. I'm going to make this just as difficult for me as you would for you. Actually, if I truly did that, then I wouldn't ever use any line tools or any shape tools in general. I would just go straight through and do that. So I'm leveling with you a little bit. I need to make this look a little bit clean, because I can't do this very well on a computer like you can on a piece of paper. My computer handwriting is dreadful, as you can well tell. Now, do I need a graph for this? No, I do not. But I do want you to confirm that your answer is what it is. Here's y equals negative 2x plus 1. I start at 1, I go down 2 over 1, over and over. And this line won't look perfect because this is not drawn to scale. So here's the original line, here's line AB. Okay. Now AB are just points that are on the line. They're not endpoints because it is a line. It's not a segment. There are no endpoints. So let's just say that A was up here, B was down here. Okay, we need to make one parallel. Actually, I want to make A over here. Let's make this parallel. Okay, it's going to pass through the point 03. Now 03 is right here. It's not very far away from it. So we know if it's parallel, then we know it's going to run looking kind of like this, right? So the question really is, what is the equation of the line? Well, they're being very, very helpful for you with all this information here, because 03 is actually a y-intercept. And if you want to write this in slope-intercept form, well, you already have your y-intercept. It's 3. It's there for you. And what's the whole thing about lines being, excuse me, about lines being parallel? Well, the slope's going to be the same. Here's your slope for one of them. Your slope for this one is also going to be negative 2. Negative 2 over 1, if you want to say that. But it's going to be negative 2. So I already know the equation of the line just through this info. I really didn't need any of this graph stuff. I already have all the information I need here. The equation of the line that I want to do that's parallel to it is going to be y equals negative 2x plus 3. That's it, and that's all. If your problem becomes more complex than that, you're going to have to deal with it, a little bit. For example, what if you already only knew the slope and you wanted to find that y-intercept? I would go with this. Okay. I'm not using point slope form for this one, by the way. You could, but this already has a point at 0. I think it's not worth it. Anyway, you plug in the points 0 for x and 3 for y. See what happens? Negative 2 times 0, it goes away. You get b equals 3. So you get the same thing. You could graph it. You could do exactly that, and you could come up with the line thing as well. The first and most important part is you see the word parallel, so you think same slope. And that's really where you have to go with this. For any slope-intercept form, you need slope and y-intercept. Start with slope. You have it. There it is. That's number 12. Okay, number 25, are these lines perpendicular? Explain. This is still in chapter 3, it looks like. So for things to be perpendicular, just like with parallel, you want to think something with regard to slope. Perpendicular is about opposite reciprocal slope. Opposite reciprocal means that the sign changes and the fraction flips, becomes the inverse of what it was before. Now your book says something different than what I say. I always refer to opposite reciprocal. I'm not convinced your book actually ever says this. Your book mentions the fact that both of your slopes, when you multiply them, you're going to get negative 1, which is kind of interesting. If you think about the slope of 2/3, not that it's one of these right here, the opposite reciprocal is negative 3/2. What is 2/3 times negative 3/2? That's negative 6 over 6, which is negative 1. So it is true. Your opposite reciprocal slope With multiplied with the other slope will give you -1, with one exception, and that is when you're referring to something like number 26, which we'll get to. Your book does mention something about vertical and horizontal lines. So what am I going to do here? What I want to do is I want to personally for myself, I want to write this in slope-intercept form. I know that if I do, then my slope will be the number that's multiplied with x. So the first one's already in slope-intercept form, and what's the slope of this one? Well, it's -1/1. -1's being multiplied with x to get -x. That's what's giving me -1/1. This one, I don't see the slope yet. This isn't written in slope-intercept form, so I need to do that. How do I do that? Add x to both sides. You're going to get y equals x plus 20. Does the y-intercept matter? No. It's not going to matter at all. It doesn't even matter if they're the same. What's the slope here? It's +1/1. 1 times x is 1. -1/1 and 1/1 are opposite reciprocals of each other. So indeed, yes, these are perpendicular. And that's it. I don't need to graph them. Once I have opposite reciprocal slope, I'm good to go. And again, 1 and 1 flip, and you get 1 and 1, I suppose. And this is positive, this is negative, so sign changed. Okay? Okay, number 26, here's where I was talking about in the book, and I think it's important to know anyway. Vertical and horizontal lines are always perpendicular to each other. Now, why do they not refer to or opposite reciprocal or multiplying and you get -1? Well, y equals 3, the slope is 0. X equals -2, the slope is actually undefined. Why? Because with x equals -2, the graph, forgive me for this graph looks like this. So pretend like that's vertical. Gosh, I should really redo this with actual lines, because then the vertical actually would matter. Let's say this is x equals -2 right here. Okay, that's a vertical line. Okay, how much is it rising? Well, it rises infinitely. But if you rose to some point from here to here, how much did it rise? You know, it rose, let's say it rose 5. How much did it run? Well, it didn't run. So your slope would be 5/0. Dividing by 0 is undefined, as you can see. With this slope being 0, it's because you don't rise at all. Let's say you ran 5. 0/5 is 0, so that does work. So anyway, if things are vertical lines and horizontal lines, as you can tell with the green one as well, that gives you perpendicular lines. So are these ones perpendicular as well? Yes. Vertical and horizontal lines always give you perpendicular slopes. That's said in the book. Okay, use slopes to find whether the opposite sides of quadrilateral ABCD are parallel. Okay, this one, it's a lot more work to do, and you know what, honestly, I don't know if I'm going to graph this one. I might have to. I'm going to do a rough graph, though. I'm not going to actually do all the tick marks things. A is at 0, 2. See, I'm just going to do it like this. B is at 3, 4. C is at 2, 7. Oh boy, way up here. And D is at -1, 5. Okay. Now here's a quadrilateral, and again, it's not drawn to scale, so you cannot go by this drawing. The point is, I want you to make sure you know which parts connect, because the idea is about figuring out whether or not opposite sides are parallel. How do we do that? We have to find the slope between 2 points. So what I have to do here is I have to compare the slope. And the other reason to draw is to figure out which slopes to compare. For instance, I have to compare the slopes of AB, that's an A, and the slope of CD. If those are the same slope, then the lines are parallel. Okay? Then I have to compare the slope of AD with the slope of BC. If those slopes are the same, then the lines are parallel. Okay? So how do you find the slopes? If you want to do general slope formula, it's y2 minus y1 over x2 minus x1. Okay? Again, not something really to memorize. It's something more a matter of from A to B, how much did I run, how much did I rise? From 0 to 3, okay, I ran 3. But you just have to make sure you know which one goes where. So I ran 3. I rose from 2 to 4. I did 2. Okay, you can see why sometimes really don't use this more than you feel like you need to. Okay, and I'm being serious about that. Right? Don't do more than because it makes you feel like it's a process. If there's something quicker, you use it. Period. you do. And just as efficient and with as little mistakes as possible. If you feel like you're going to make mistakes, okay, that's a different story. Now, that was from A to B. What I really should do, though, is I should be looking at, not from C to D, I want to do from D to C, just so I'm talking about run and rise the same way. So from D to C, I'm going from -1 to 2. Okay, that run is 3. The rise goes from 5 to 7. That rise is 2. Whee! Parallel. These two are. We still have to figure out the other ones. Are these ones parallel? Okay, I'm going to go from A to D, then B to C. It looks like that's the same run, negative run, positive rise. So let's do from A to D, from 0 to -1. That's a run of -1. A rise from A to D is from 2 to 5. That's a rise of 3. That's -3 as a slope. Okay, B to C, that's going run from 3 to 2. That's -1. Okay. And then the rise is from 4 to 7. That's 3, which is also -3. Same slope again. Whee! Parallel. But again, did I use this formula? Well, the formula, yes. I mean, I didn't plug things in. I didn't say, let's memorize it and do it. I just said, how much did I rise? How much did I run? It's a simple counting measure. And if you have a graph, you're even better off. And if you have smaller numbers, it's totally fine to do what you're doing. Will I use this time to time? Absolutely. If the numbers were 167 and 0.24 and all that stuff, yeah, I'm just going to plug it in and be safe. But when there are things you can say out loud, do yourself a favor. Save time. Be efficient. And also, look, there's this minus stuff. What's to say you won't accidentally do 2 minus 1 going from C to D instead of 2 minus -1? What's to say you won't? There's nothing to say you won't. I've seen it happen a lot. So just got to be careful. Okay, number 35. If triangle cat is rotated 100. Okay, chapter 9, by the way. Chapter 9, transformations. Only got a few problems with this one. If it's rotated 180 degrees about the origin, what are the coordinates of C prime specifically? I don't know how much I'm going to say about transformation stuff or with rotation stuff here, because I would talk to you about rotating your paper, okay, like 180, whatever, but I can't rotate this one. This is actually glued and scanned with this problem. So I could rotate the entire problem, flip everything upside down, but I think you can be a little better than that here. Let me tell you where C would go if it rotated any 90 degrees. 90 degrees counterclockwise, okay, C would rotate from here, from 1,4 to -4,1. How do I know that? Practice it a little bit. Turn your paper, you kind of see that. It's in quadrant 1. Where does it go? After that, it goes in quadrant 2. It lays close to north. Now it's laying close to west, x-axis here. It goes 90 degrees. It's going to go from here down to -1, -4. This is where C prime actually is going to end up. This would be your final answer. B, you had other options. And I mean, it didn't have to be a multiple choice problem. You could have looked at it some different ways. Now, if I went clockwise instead, here's the thing. I went 180 degrees counterclockwise. Well, 180 degrees clockwise is the exact same thing. So let's go 90 degrees and then another 90. Let's figure out where we land. So going this way instead, if I go 90 here, I'm going to end up at the point 4, -1. If I go another 90 this way, I'll end up at -1, -4. What I could do for you to kind of maybe convince you more of this is I really want you to think of distance formula. Okay, distance formula. I'm sorry, not Pythagorean theorem, which is distance formula. But Pythagorean theorem is the square root of a squared plus b squared. Right? If a squared plus b squared equals c squared, then c equals the square root of a squared plus b squared. Okay. When you're rotating about the origin, you have to make sure that your point stays equidistant from where it was before. So, if I ended up using a compass, okay, any of my points would have to stay the same distance away than they were previously. What that means is if I plot, let's see, how am I going to do this right? If I find the distance here between 0 and C with the compass, looks like this might just about do the trick right here, and I draw all around where are my other points. Assuming this picture's drawn to scale, which it was scanned, so there could be some inconsistency. Where are the exact points that this lands on? Well, right here, right here, right here, right here, right here, right here, and right here, and right there. Now, in terms of rotations, though, it's rotating about the center here. I want you to take a look at where these rotations are actually coming into play. C through the origin would give you there. A 90-degree rotation would be one that's perpendicular, opposite reciprocal slope. These are the only points that I'd really be looking at. It'd be hard to come up with whatever rotation this is to get you there. I'm not really concerned about that one. But these are the only ones here. Now, what was I talking about with the Pythagorean theorem? Well, over here, I have right triangles. Boom. What's this one? Square root of 4 squared plus 1 squared, right? I don't care that this is negative. I just care that it's 4, right? Because when I square it, it's still going to be 16. Here's square root of 4 squared plus 1 squared. Here's square root of 4 squared plus 1 squared. And right here as well. So you can kind of see where those distances come into play. This ain't really a magic trick. All these numbers, when rotated about the origin, you'll use the numbers 1 and 4. That's why they're there. So it's just a matter of where are my 90-degree rotations? Where is this right angle being made? Right there. There's a right angle, and then another right angle here. Gives you that one there. Probably overkill for this problem. You're probably looking at this and saying, what the heck are you doing, Mr. Robinson? I'm trying to give you perspective. I really am. I really want you to understand this more than just rotate the paper, just use patty paper, just follow a rule. By the way, there is a rule. When you rotate 180 degrees, if your original point was XY, after 180, you know what it'll become? So we could have gone straight from there. But is that the important talk? No, because it could have been rotated about another point that wasn't the origin. It could have been rotated about a different center. It could have been 90 degrees. Really want you to make sure you know all of them. But one most important thing amongst all of this is that in your rotation, it should be equidistant. So what I am going to do with this problem, though, to do a little bit more is I'm going to give you all the points of C prime, A prime, and T prime. C prime would have gone here. A prime would have gone here. And T prime, 180, would have gone here. You can connect them, and here's your rotation. Now, this rotation also would have been the points for your reflection, with the exception of across this line here. With the exception of C prime would have been here, T prime would have been here. A prime would have been exactly where it was. Okay, let's do a reflection across the x-axis. Now, what I'm not particularly fond of with this problem is I do like to graph these ones. However, I'll do the best I can without it because it's I mean, I'm not saying it's hard. I'm just saying that I do like to plot them. One thing that I do want you to understand for sure, especially if this is a multiple choice problem, is know which problems are wrong first. If I'm reflecting across the x-axis, I'm in quadrant 3. If I'm in quadrant 3, that means my x and y values will both be negatives. See ya, A and B. You're gone. Okay, what I also know is if I'm reflecting across this axis here, C will be closer. I mean, I can tell you what the exact point is right now, and I'm sure you could as well, but I know that C will be closer to, C prime will be closer to the x-axis than either A prime or B prime. I can also tell you that A prime, B prime will be at the same height away. So whatever they are, they should be the same. Okay, so A prime, B prime are the same on these two. The question is, which one will be C prime? Will C prime be at -6 for y or -2 for y? Well, it's going to be closer to the x-axis because when you reflect, this is 2 away here. This is also 2 away here. That'll be 0 minus 2. It is going to be it is going to be D. -2 there. Boom, that's your answer. I won't go much farther than that as far as reflection, other than you count how far you are across from here and repeat that over on this side. Apparently, they didn't want us to graph this problem, so I won't either. I'll go with their methods of multiple choice. Number 36, which statement is true about the figure at the right? It has no rotational symmetry. It has no reflectional symmetry. It has rotational symmetry with an angle of rotation of 45 degrees and reflectional symmetry with 6 lines of symmetry. Okay, I'm going to go ahead and debunk the fact that it doesn't have either of these. I do believe that it does have both of these in the case of when I do rotate this a certain amount, meaning when I rotate this amount right here I will have created the same objects that I did before. Now, how many rotations does that take? 6. So what's the angle of rotation? Okay, really that's the question. How much am I rotating each time here? What is that? Well, if there are 6 of them, and they're all, you have to assume this is a regular, star, 6-sided star, 6-pointed star. So if there are 6 of them, and all these angles together add up to 360 degrees, that's a full circle, then each one is 60. Which means this has a rotational symmetry at 60 degrees, or an angle of rotation, 60 degrees. So C is out because that's 45, so it must be this one. Let's check and see if it does have 6 lines of symmetry, really. I kind of technically drew 3 of them, but let's redraw them. I'm going to use the line tool this time. Okay. Now, like I said, I think we know that we're right. Let's just find them. Here's one. Tilt your head down the line of symmetry I'm showing you. There's one. There's one. Tilt your head down that one. Check it out. There's one. Hopefully you can get a horizontal perception with these lines here. There's one. There's one. And there's one. Actually, that looks pretty cool. I'm actually getting this illusion. I'm not sure if you're seeing it, but I'm seeing like green circles within here. Whoa, that looks cool. They're kind of lighter. I don't know. Maybe I don't know what I'm doing. But there you go. There are your 6 lines of symmetry. It's got to be D. It's gonna be D. Number 30. Oh, it's not number 37. Okay, that was it for chapter 9, actually. Here's chapter 4 now. Write a congruent statement for each pair of triangles. Name the postulate or theorem that justifies your statement. Okay, I'm not going to do 2-column proofs, but you're given some things. These angles congruent. These angles congruent. What I need now is a side that's either outside here or inside here, and then I'll be good. Triangles will be congruent. So any side will do. Looks like MO could be congruent to itself by the reflexive property. What that really means is that it is a shared side in both triangles. As you can see, it's kind of a reflection. And it's a shared side and it must be equal to itself because it's the same thing. Okay, so that does mean that triangle, what's the statement? If I say MOP, because I like the word mop, that's congruent to, remember, it's reflection, MOP. This will be MON, like Monday. Now, Y, that is angle, side, angle. I have angle, congruent, side, angle with angle, side, angle. Boom. That's number 13. Number 14, I have given angles here that are congruent. Once again, you could do this reflexive property stuff right here. That's good to go. And I have parallel lines. Now, what I do have here is a transversal. This thing acts, I don't know if you need me to draw this. I guess I will. They'll be dotted though, so you have to bear with me. These 2 parallel lines, they're cut by 3 different transversals. Here's one, which doesn't help me here because here's an angle, here's an angle. That's not really doing anything with both triangles. Here's one, which doesn't help. This one does help, right here. It's drawn down the middle. It looks a little different for you guys because this one's diagonal and slanted, but that makes... Now, here's what it doesn't make. It does not make these 2 angles congruent. Why? Because I don't know these 2 lines are parallel, UT and SR. So you got to be careful about which ones you make congruent. These ones are congruent because here are your parallel lines with your transversal. So those 2 are congruent. If I delete the lines now, those big ones, take a look at where these were made within your triangles. Okay. Now this one works more as a rotation than a reflection. If it was a reflection, then this would have been congruent to that, which is not the case. But so what I do have, I should make these different marks though. Angle RTS is congruent to angle UST, okay, because those are alternate interior angles, okay. If that's the case, I do have angle, angle, side with angle, angle, side. Now it's a good thing that I made my angle congruent statement good enough that this actually is a these parts correspond. Triangle RTS is congruent to triangle UST by angle, angle, side. It just so happens that is congruency conjecture, or property. Okay, here I have W congruent to Z, angle ZVY congruent to angle WVY. Those are given. Reflexive property one more time. Boom, boom. Good to go. I have angle, angle, side, angle, angle, side, triangle, ZVY is congruent to triangle WVY by angle, angle, side once again. Now, if it was angle, side, side, no good, right? Side, side, side would be good. HL would be good. Angle, angle, right? It depends on what you have. Definitely working with that. That was almost it for triangle congruent stuff, or so it seems. We're just going to keep moving along here. This stuff is within the chapter, though, I do believe, and this has to do with isosceles triangles and equilateral triangles. What's true about isosceles triangles is that when you have, you'll have two congruent sides, a pair of congruent sides, and the angles opposite them will be congruent. So the angle opposite this one is this angle. This is congruent to this side right here. Okay. So if this one's n, then this one's also n over here. Now you're saying, well, why does that matter? It's not helping me. You're not getting any farther from me, Mr. Robinson. Well, I can. N here and n here and 126 here give you 180. That helps, right? Yeah. So that's two n's, and I subtract the 126 over here, I get 54. You're going to get n equals 27. So both of these n's are 27 degrees. You might say, well, how does that help us find m? You know, it can a little bit, because you can do it this way if you'd like. These are both 27. What I could do is look at this big right triangle right here. Okay, I could say one angle's 90, which makes this one plus this one equal 180. Now, what is this one right here? This is m plus 27. So m plus 27 is one angle, plus 27 in the other angle, that equals 90 degrees. So that makes m equal to 26 degrees. Okay, what's another way we could have found m? Possibly more simply, depending on how you're looking at it. You could have used m without looking at n at all, and n without m, etc. We could have done same thing with n as we did. Anyway, 126 plus this angle, let's call it x, equals 180 degrees. Right? So this x right here is 54. Now, where does 54 come into play? Here's a right triangle. 54 plus m. I'm sorry, this is 36 degrees. I can't even add. Anyway, that's 36 degrees. 54 plus m is 90, so m is 36. Sorry about that. Little hiccup. That's what I get for going too fast, right? And don't go too fast. Okay, 31. I have an equilateral triangle, as all those are congruent, which makes all these congruent as well. Furthermore, they're not just congruent, they're all 60 degrees. You have to imagine that that's coming into play for this thing. 60 degrees will help you find most of these things. I'll probably work the fastest way out of this one, but because I don't think we ever looked at special quadrilaterals, I am going to do a different way as well. These are all 60 degrees. This is a right angle. That makes n 30 degrees. How? Come on. You know how. You know how. If that's 30, m right here, 30 plus m is 90. Okay, once again, same idea as before. So m is going to be 60 degrees. Going faster with that problem, I gave you those. So let's just write those answers out first so you have them in play. Okay, let's find a different way of going about it now. I'm going to go back and erase this stuff. Okay, let's start with that 60 idea here. Okay, now this on the outside represents a 1, 2, 3, 4-sided shape. It's a quadrilateral. So what do we do with a quadrilateral if we try and think about what's the interior angle sum of a quadrilateral? Two 180-degree triangles, that gives you 360. So 60 plus 90 plus 60, or 60, 90 plus 60 plus m equals 180. Now you might ask yourself, why didn't I call this 60 plus n? Well, because if you did, you'd have two unknowns in one equation. Now I could solve for n, like you're going to solve for n the same way as you did last time, right here. But solving for m, here's a different method. 90 plus 90 is 180. 60 plus 60 is 120. 180 plus 120 is 300. Oh, see, I just did this wrong too. This is 360. Equals 360. I was too focused. I don't know what I was focused on. So m is 60. And once again, n is 90 for the same reason. So you get m is 60. Once again, doing that stuff. Good to go. I don't think I'll be doing all the different problems like that, but I already see a quadrilateral in this next problem that I think I want to do. I'm going to erase this stuff so I can save some room. Okay, number 32. M is this corner angle right here, okay? Just so you're aware. N is right here. All right, here I have an isosceles right triangle, which is very unique. If this is n, then so is this right here, because the triangle idea. Now, in an isosceles right triangle, one angle is 90, the other two are congruent to each other and add to 90, so they must be 45. N equals 45 degrees. I'm not even going to spend a lot of time talking about that one there. You have that. So this is n, this is n, this is m. This must also be m because you have an isosceles triangle. If this is m plus n, this is also m plus n. Now, n is 45, so I can work with that 45. I can do something like that. So I can do 50 plus the two angles. There's m plus 45, and there's another m plus 45. That's going to equal 180. I'm looking at the big triangle here. 50 plus m plus 45 plus m plus 45 equals 180. So I can go that way about this problem. I'll show you a second way in a moment. That's 140 plus 2m equals 180. So 2m equals 70 and m equals 35. That's that small angle right there. Okay. Here's a second way of looking at that problem. What I could do is I could solve for n and m independently, completely differently from one another. What if I look at this? Of course, I have the dashed lines. What if I look at this shape right here in red? The little arrow or Pac-Man or whatever you want to call it. That's a quadrilateral. And it doesn't matter that it's a convex or concave or like whatever you call it. It doesn't matter if it's that kind of quadrilateral. What matters is if you did recognize that this was m for the sake that this one's n, so this one has to be, isosceles, yada yada. This angle right here is the opposite of 90 in a 360 degree thing. This is 270. So I could do 50 plus 2 of the m's plus 270 equals, now in a quadrilateral, still the interior angle sum is still 360. So then you'll get 2m, let's see, 50 plus 70. So I did something wrong in one of these problems. I think it's the other one. How good is the video when I show wrong answers? Let's take a look at what I did here. 45 plus 45 is 90. 90 plus 50 is 140. Somehow I got 70 here. Don't even ask. Really don't. I divided by 2. I don't know what I'm doing. So m is 20 here. So again, this is why I double check problems. This is why it's 7:45 at night. This is too much for me. All right. Hopefully you guys are getting more out of this than I am because my brain is cooked. All right. Moving on. Are the polygons similar? This is chapter 7. This is unit 5. I'm actually making good time. I'm just talking, man. I'm just talking. Are polygons similar? So, if so, write a similarity statement and give the similarity ratio if they are not explained. Okay, there are a lot of different things that we have to talk about with this problem type, especially with regard to what kind of problem they'd give you with this. It would be very, very bizarre if we found one way for the polygons to be similar, for the triangles to be similar, and another way that we tested that it didn't. So I am going to test that and see if that happens. First of all, for polygons to be similar, the difference between similar and congruent is congruent means angles and sides are congruent. Similar means angles are congruent with sides. There is a similarity ratio that you can find. We could set up a proportion from one triangle to the next. Now, the only way that that's going to work really is if you make corresponding parts line up well. And that's what I always love to do first. Even for myself, I honest to God, even if I was doing this on my own test, like my own, I would be redrawing this little triangle right here, and I would correspond parts. How do I know what parts correspond? The angles, man. F is congruent to A. There you go. That's where F sits. I'm not even going to draw the angle. The only good it had, yeah, let's do it. But the only good it really had is to know what parts correspond. B and E correspond. And you can go by the looks a little bit. Looks like they look like they'd be here. And C and D. So if anything, this almost looks like a reflection of what it was before. So what are the side lengths? This one's 6.0 or 6. This one's 2.5. And this is 4.5. Okay, first of all, there are 3 different similarity statements that we'd make to say that they're similar. If we could get any sets of these, we'd be good. I have a good feeling we can get all 3 of these, but I'm going to check these in order. I'm going to start with angle. Angle A is congruent to angle F, check. Angle B is congruent to angle E, check. Let me write these. Now those are given. All of these are. Now, I did not need to know that angle C was congruent to angle, this should be a D. I did not know that angle C needed to be congruent to angle D. What I did need to know was that these 2 sets were congruent, therefore these ones have to be congruent. I'll go ahead and write them. But it's not important. All you need are 2 sets of angles. You're good enough. The 3rd angle is then assumed to be congruent. So, yes, these are similar by this one alone. I should not have to check the other ones, but because there are lengths, I will, and especially because I don't know how many similarity things I'm going to do, I want to tell you something about similarity. So in terms of this, how do I set up proportions? Parts need to correspond. Here's how I'm going to say it. The long side in the big triangle is to the long side in the small triangle, as the short side is to the big triangle, as the short side is to the small triangle, as the middle side is to the big triangle, as the middle side is to the small triangle. Notice how the arrows went. Notice how I said it, how the units lined up. I'm going to test all of these, and I'm going to use my calculator and see if I get the same similarity ratio for all 3 of them. Then side angle side would work, and side side would work. I'd kill 2 birds with 1 stone. Let's start with just big side and big triangle to big side and small triangle. Let's see if that's equal to small side in big triangle to small side and small triangle. I'm going to start just with those. Then I'm going to say side angle side would work because angle A is congruent to angle F. The angle in the middle, the angle in the middle of the sides that I'm setting up, what am I doing? The angle in the middle of these 2, side, angle, side. Now what are these sides? They're not congruent. They have the same similarity ratio, or do they? Let's check. 8.4 divided by 6 gives me 1.4. 3.5 divided by 2.5, and I'm using a calculator for this. I don't dare do anything. That's 1.4 as well. So side angle side also checks out, meaning the ratio of this to this is the same as the ratio of this to this, and the angle in between them is congruent. So side angle side is good. Does side good? All we have to check, ignore the angles. Would is 6.3 divided by 4.5, the same thing. Now what would be really interesting is if they gave us a problem where the angles were marked congruent but the sides weren't the same. That would be really kind of be stupid, because that would mean they're not similar, and the angles therefore could not be congruent. Checking my calculator, I am getting 1.4, so it's a good thing those things check out, which means side also works. You could use any of them for any sort of reason. So let's do a few things. I'm still not done with the problem. Similarity statement. I need to state which 2 triangles are similar. ABC. And it's not DEF, it's triangle FED. By any of these, any of the reasons I found out works. Now, we still need a similarity ratio. The one I can do, I mean, you can use decimals, I suppose, if you want. I'm not really keen on those. Normally they use integers of some sort. So if I could, and I don't know what the answer in the book says, I could say that from large to small, the ratio is 1.4 to 1, meaning any side length, if there was a side length in this big triangle that was 1.4, the side length over here would have been 1, right? It's shrinking from large to small. Or 14 to 10. That would be a more appropriate, or I guess that also makes what? That makes 7 to 5. Or 7 to 5. I'm sure this is what they say in the book. Or 5 to 7. Not arrows, colons, darn it. 7 to 5. 14 to 10. There we go. That's a good similarity ratio from large to small. Small to large would have been 5 to 7. Okay, the polygons are similar. Find the values of each variable. Okay, they are similar. So now we don't need to prove it. And I don't know if we could. 'Cause these aren't exactly triangles here where you can only do angle, angle. You need a little bit more. Okay, the parts that correspond are already lined up. You can see bottom left angle is the same, bottom right angle is the same, small guy on top, etc. So the question I'm going to ask you here, because I'm not going to spend a lot of time on this problem. There are some problems you don't need to spend as much time on. You could do this whole similarity, 10 is to 5 is blah blah is to blah blah, and you could cross multiply, right, as like 10 is to x and do all that. Well, it's not 10 is to 5, it's 10 is to x. 5 is to 10 as 10 is to x. And cross multiply. You're wasting your time with a problem like this. What multiple? What do I have to multiply 5 by to get myself 10? 2. What do I have to multiply 10 by to get x? 2. X is 20. What do I have to multiply y by to get 35? 2. So what do I have to divide 35 by to get y? That's the question. 2. So you might do some cross multiplying depending on how familiar you are with this. Z and 15, same idea. 15 divided by 2. Oh man. There are your answers. You're good to go. So again, you could do cross multiply, set up ratios, do the arrows thing. The way that I talk about them, I said I won't spend time on this problem. The way that I talk about them is saying something like left side in small quadrilateral is to left side in big quadrilateral, as top is to small quadrilateral, top in big quadrilateral. So you can do z over 15 equals 5 over 10. Stuff like that. You'll solve for all of them. You'll get your answers. Or base and right side and right, anything like that. You're good to go. X, Y, Z. Okay. Okay, a map has dimensions 9 inches by 15 inches. You want to reduce the map so that it will fit on a 4 by 6 inch index card. What are the dimensions of the largest possible complete map? This is actually the key word in this. That you can fit on the index card. Okay, the thing that you might, let's see, I want to make 9 my height. The thing that you might be assuming is that these are the same ratio. And you would be wrong to assume that. I'm not saying it's true or untrue. I'm saying you'd be wrong to assume it. If this is 15, and this is 9, and this is a map of something, whatevs, I have something else that's 4 by 6. Where's my thing? So I have something else over here. It's 4 by 6. It's obviously smaller. Now 6 I'm going to make wider, like I said. Now, in terms of this ratio, what I'm going to show you is that these are not necessarily the same. They could be. I really don't think they are. I don't think they are. Whenever you're looking at a TV, they do width divided by height, and you get some sort of aspect ratio. I want you to go to your movie library, wherever your DVDs or Blu-rays are. Go find a movie. Go try and find this number somewhere. Or go and try and find this number somewhere. Or sometimes even try and find this number somewhere. If you have the Blu-ray of Frozen, it's got some weird, I think 2.2 by 1, something like that. These are the, oh, I'm sorry, there's one more you'll find. Try and find this number somewhere. I think it's 8.5. All these aspect ratios are the things that your width by your height is measured in. The bigger the aspect ratio is here, the wider your picture appears, meaning like the more black bar on top and bottom. 178 by 1 fills up your entire screen. If you have an HD TV, your aspect ratio is probably 16 by 9. Try 16 by 9 on your calculator. I'm going to try it right now. and you're going to get 1.77777, etc. That's what this number is when rounded. So that's what they're referring to. Anyway, so what I'm saying is you can do an aspect ratio. Let's do 15 divided by 9, and let's do 6 divided by 4. Let's see if they're the same thing. Let's see if they have the same aspect ratio. I'm not saying these are TVs. 15 divided by 9 is 1.666667. That reduces, obviously, if you divide these by 3. Really, what you should do is just reduce the fractions. This reduces to 5/3. This reduces to 3/2. These are not the same thing. So not the same aspect ratio. So what does that have anything to do with this? Well, you want to make a little assumption that you're just going to shrink one and then automatically you'll be good with the other. What this problem is all about is you got a map, and it's this big. And what you has to do is you have to make it small enough so the whole thing fits. So the real question when you do aspect ratios in a certain way here is which aspect ratio, or sorry, not aspect ratio. I'm going to shrink 15 down to 6. I should do this the other way. I'm going to shrink 15 down to 6. I'm going to shrink 9 down to 4. What multiple, like what do I have to multiply 9 by to get 4? Well, you got to do 4 divided by 9 to figure that out. And what do I have to multiply 15 by to get 6? I have to do 6 by 15 to figure that out. The question here is, remember, I have to get a complete map of this, and I have to shrink it on the index card. So the question is, which ratio will I use? Will I use 4 divided by 9 or 6 divided by 15? The answer is the smaller one. Whichever one is the smaller one is the one that's saying that's the one that's going to fit completely onto my map. I'll kind of give you the reason when I kind of calculate these. These don't equal each other. We're just trying to see which one's bigger, which one's smaller. 4 divided by 9 gives me 0.444444. 6 divided by 15 gives me 0.4. 6 divided by 15 is smaller. 4 divided by 9 is bigger. I want to choose 6 divided by 15. And really, here's why. What I'm going to do is I'm going to shrink 15 down to 6. I'm going to shrink 9 down to 6/15 of 9. Okay? 6/15 of 9 will be smaller than 4/9 of 9. 4/9 of 9 is 4. 6/15 of 9, and notice I'm not doing proportion stuff. I could say, okay, this one's going to be 6. What's this one going to be? Let's call it x. So I could have done x over 9 equals 6 over 15. You cross multiply it, you do all that stuff. You're going to get right back to where this is. So 6/15 of 9. Now, I shouldn't be that condescending about it, right? You're trying to figure out how to do this stuff. But I need you to think of ratios as more than just proportions and cross multiplying. What you're doing is we're taking 6/15 of each value. And to take 6/15, you multiply by that amount. 6/15 of 9 is 3.6. So the idea here is 3.6 inches will fit on here, because that's less than 4. My complete map will fit on my card. Will I fill up the entire card? No. That's not what I'm trying to do. What I'm trying to do is make a complete map that's big enough, the largest possible one. So it's going to be 6 inches wide. It's going to fit on the entire card this way. This way I'm going to leave some white space, either on bottom or on top, or I'm going to make it in the middle, all that stuff. Now, what would have happened if I did 4/9? I think that's the bigger question here. Why couldn't have I done the other one? Well, because here I would have taken 4/9 of 9. That would have given me 4, so it would have been this tall. What's 4/9 of 15? The problem is it's more than 6. 4/9 of 15 is 6.66666, whatever. There's another 2/3 of an inch sticking out right here. That won't fit on the card. So that's the issue. You have to pick the smaller one because it's got to fit on there. So you got to compare the two and decide, okay, which one gives you a smaller amount. Choose that one, because that's what will make both of them fit. So that's the idea behind that one. I was going to ask any questions, but then I realized I wouldn't get an answer from you guys. So that's number 18. Okay, 6 and 7. These are actually, this is a brand new thing. This is area and perimeter. So that was Chapter 7. Chapter 7 is now done. This is problem 6 and 7 on perimeter. They're kind of asking the same, they're different questions, but they're asking the same kind of question. Answering 6 will help you answer 7. I have a rectangular certificate that's 8 inches by 10 inches. So looks like they really like to do widths second. I don't know why. I assume the certificate, actually I can't assume the certificate's this way. But going by what they talked about last time with an index card, I never do maps tall. I always do them wide. They have a frame that's 1.5 inches wide surrounding it. What that means is it's 1.5 inches every direction. So now this is a problem that would have been great for like what are called math contests. I'm sure you haven't done those before because I don't think we offer them at this school. AMC contests, stuff like that. These are problems that, I mean, there's no, have I taught you this kind of problem? No. But come on, like you have to know this kind of problem. Well, you know what? I haven't taught you area and perimeter at all, really. But the idea is that it's 1.5 inches in each direction, and they're trying to ask you what the perimeter is on the outside the frame. So this going across is 1.5. So is this way. By the way, so is this, and so is this. I guess the thing is that you have to know what it is that it's saying when it says 1.5 inches around it. And I'm only guessing this is what it says. I never checked the back of a book or anything like that, so I might be wrong. But these are also 1.5 inches. So what's the perimeter surrounding it? Well, this width now, this was 10. Okay. But this is another 1.5 right here. This is another 1.5 right here. So the entire width is 10 plus 2 1.5s, that's 3. So the entire width is 13. The entire height is 8 plus 1.5 plus 1.5, which is 8 plus 3, which is 11. So is perimeter base plus height? No, you got to add up all the sides. So 13 plus 11, and it's rectangular, so 13 plus 11 times 2, which is 24 times 2, which is 48. Don't know why I wrote a 2. 48 inches across. You could also find out the area of the frame if you wanted to. I guess they didn't ask us to. Someday I might ask you to do that in a certain way. It would actually be a great question for me to ask, and I don't know why I'm not doing it. I guess I'm just time conscious. Here we go. Same thing with the garden. A garden is 5 feet by 6 feet, and it has a walkway 2 feet wide around it. So same idea of a problem, as you can tell here. I think the idea is that you're supposed to do one of these. They help you do the other. So here's 6 feet. Here's 5 feet. Okay, same scenario. Your garden, I'm just going to draw another rectangle around it. Your garden, or your walkway, the garden's on the inside, because gardens are green like that. The walkway is 2 feet each 2 feet width. So 2 feet here, 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 here. Find the amount of fencing needed to surround the walkway. So that's a perimeter question. How much feet of fencing would I need across here? So the width is 6 plus 2 plus 2. So 6 plus 4, which is 10. The height, I don't know, I'll call it length, not height. The height is 5 plus 2 plus 2. It's 5 plus 4, which is 9. So add the width and length twice. 10 plus 9 times 2 gives you 19 times 2, which is 38 feet of perimeter fencing. Cool, cool? I think that makes sense. We could have found the area here, but let's do area of this one, perimeter and area. Find the perimeter and area of each figure. We're just doing one figure here. Congruent marks help you out. If this is 5, and this is also 5, you start filling these things up. It'll help you a little bit. This is 3, this is 3. Here's another 5. Ooh, congruent, you got that. And this is 3. So perimeter is just adding all these up. I'm not even going to write them. You know what to do. Start somewhere. I'm going to start at the head right here. 3 plus 5, which is 8, plus 3 is 11. Oh, I'm not done. I'm sorry. Here's a 3. Here we go. 8, 11, 14, 19, 24, 19, 24, 29, 32. 32 inches of perimeter. Area is a little different. What you're going to have to do here is divide this into 2 different rectangles. In this case, this one's a square. Find the area of each individual thing here. This is 5 times 5. That's 25 square inches. This one's 3 times 5. Don't be fooled by that 3. This one's 15 square inches. So it's going to be 25 plus 15, which is 40 square inches. And that's just the idea behind it. You just you add up areas. That's kind of how area works, is the coverage of those things. Like I said, the perimeter, the area of this stuff would have been much more interesting problem to do. So how would have I done that? I would have either looked at dividing these into rectangles, maybe like that, you know, whatever, into any sets of rectangles and add them all up. Or little squares here, find those little 2 by 2 squares are 4, stuff like that. There are a lot of ways. I could have taken this big area and subtracted the area of this. Fun ways to do it, right? But it's not asked, so I'm not going to do it. Okay, I got a few sets of problems left. They're all construction, and then that'll be it. In exercises 1 through 8, draw a diagram similar to the given one. Oh, okay, so they're already given. Then do the construction, check your work with a ruler or a protractor. Okay, so what I'm not going to check it, but what I am going to do is construct segment QJ so that it's TR minus PS. Now, the segment addition postulate, I'm just going to help you out here for a second. Segment addition postulate says that if I add, whoa, let me keep that locked in place. If I add this segment with this segment here, I get the length of both those segments together. Now, what if it was subtraction? Segment subtraction postulate, still the addition postulate, but the other way around. If I do the long length minus the small length, what's left? Well, what's left is just this part right here. Okay, so what I'm going to do is I'm going to find the length of TR, find the length of PS. I'm going to take that length of PS, take an endpoint of TR and mark it somewhere, and then the rest will be QJ. That's all it's going to be. So, how do I do this? What I'm going to do to copy a segment, just like any other one, I start with a long segment. Then I bring in my handy dandy compass. Okay, because this stuff gets kind of awkward, because the compass thing's so big, I have to flip it over. I have to find the length, the total length of TR, which is about right here. Okay, from this end right here, I'm going to go ahead and mark this arc right there. So TR right here is also right here. And I know that looks a little deceiving, right? Doesn't this look shorter? It looks shorter to me, probably because this gets a little longer here and there's a long segment, whatever. Anyway, TR minus PS. Now what I'm going to do is I'm going to subtract the length of one of these ends, doesn't matter which one, from this length of PS here. So let's find the length of PS. Okay. Let's go ahead and go to an endpoint. What do you say we go to the same endpoint we did before? When I subtract this right here, the length of QJ is right here. It's not perfect, but I guess that's why they said confirm your findings. So that's QJ right there. Well, that's segment QJ, and that's its length. That's all you had to do. TR minus PS. Okay, construct angle F so that the measure of angle F is twice the measure of angle C. This is going to be a little interesting because I really need some room for it, I suppose. And angle C is angled in such a weird way, I'm probably going to have a little bit of trouble. But what I'm going to do is start with a segment. I'm going to copy this angle twice. I'm going to start by doing it once and then do it a second time. So there are actually, there are probably quicker ways to do this than I am even thinking about. So I'm actually going to work with this right now and see if I can actually run into a way that I want to try and make this happen. So what I'm going to begin by doing with this here is I'm going to draw an arc. The vertex will be on angle C. I'm going to draw an arc in such a way that it crosses through. In fact, I'm going to make it thin. I'm going to draw an arc in such a way that it crosses through both the sides of C. I'll make it thin so I know exactly where that vertex is. I'm going to do the same thing over here. Okay. Unfortunately, this gets really wonky. Same thing over here. Place this arc right here. This vertex will be called angle F, remember? Draw the arc with the same exact width. You need to keep that same exact width as before. I'm going to draw it pretty big because I feel like there's something I can do to make this a little easier where I don't have to copy the width twice. I'll show you what I mean. My next thing I have to do is I have to find the width between these two endpoints here. This one right here and this one over here. Once I find that width, and it doesn't look like it's going to end up being perfect, that's actually not bad. Once I find that width, okay, I'm basically going to be drawing one of these. I'm going to be drawing it over here though. Okay, I'm going to be drawing it so that, boy, I really, let me scroll down. I'm going to be drawing it right up in here. So if this is where that goes, the width intersects, boom, right there. Okay. Now, what I could do next is I could draw a line, and this would give me the measure of angle C. But what do I want? I want twice the measure of angle C. So what I'm going to do, actually, I'm going to skip drawing this line. You know why? Because this intersection right here marks the arc, right? It also marks the intersection right there. All I need to do, take this away, all I need to do is place my vertex. Now, I don't know if I ever did this the last time I talked about it. Place my pivot on that point right there. That acts as that intersection point. Because I drew my arc big enough, and because I still have the same width on my compass, all I need to do is just another one of these. Whoops, another one of these. Boom. That intersection point is where two of these go through. Right? Here's one measure of angle C, like this. But here's two of them added together, angle addition postulate. Boom. There's the measure of angle 2C, and that's angle F. Okay. So measure of angle C must be really close to 45 degrees here, because this is really close to 90. And of course, there's double check involved. And of course, also, this doesn't quite intersect at that line thing. So not everything's going to be perfect. Do the best you can with the tools you have. I have some software that doesn't give me everything I need. Okay, I believe this is the very last problem, and then we're done. So I almost got this in 2 hours. Woo! Let's see if I actually can. Construct a right triangle with legs of lengths A and B. Okay, right triangle. So right triangle means right angle. Means I need lengths A and B. This actually won't take very long. I start with this one. I'll go ahead and make this the longer one, the one on the bottom here. Okay, B, let's find that length. Let's get a little more particular and exact. Yeah, what do you say like that? So B is going to be right here. Okay, here's this length. Okay, here's what I need to do. I need to make a right angle. And, oh, you know what? I'm going to start with the right angle. That's going to be a little quicker and easier. So restart. You know what? I'm not going to start with the right angle. What I'm going to do is I'm going to place a point right here that's not over here. See, the problem with what I did before, here's kind of my thought process. The problem with what I did before here is this is B. Oh, you know what? I can do that. Okay, here was my... You're like, what are you doing, Mr. Robinson? Here's my thought process. If I made this length B, I was thinking here's going to be my right angle, and here's going to be length A, etc. The issue was I can't make a right angle unless I extend this leg. So I was thinking I'm going to make the right angle first, then do length B. And I was like, that'll make this leg really long. So I just said, let's do this, because what I can do is I can make the right angle over here. That's fine. There's nothing wrong with that. Now, why do I need some side length over here? To make my right angle. How do I make it? Well, what I need to do is I need to make this point here a midpoint of two other points. So how do I do that? I just take this compass, fix it at some width, doesn't matter what. In fact, this looks pretty good from here, right there, and right there. These two arcs have intersecting points that are now endpoints that make this the midpoint of that. Okay. Now, keep in mind, length B is still right here. I'm still good to go. So I'm going to keep that. What I'm making right now is a right angle. So let's go ahead and extend this a little farther. Let's make these two arcs here and here intersect. Boom. And what I need to now do is draw a segment that goes through there. Wasn't bad. Actually, it's pretty good. And that is my right angle. Now what I need to do is I need to make this side length A. Okay. Now this isn't a rectangle or anything like that. It's just a right triangle. And A looks like about this width right here. So let's do a different color. Let's go back to good old trusty green. Okay. And as long as I made it big enough, there's A. That's the length of A. That's where it intersects. So here's A. Here's the end of B. All I have to do now is just connect them, right? I'm just making a right triangle. I'm not making a square, a rectangle, or anything like that. And voila, there you go. So what happened? This is my right triangle of legs lengths A and B. This one is A, this one is B, this one is the right angle there. That's it. I hope this stuff was good and helpful for you. Can't guarantee that all these cover all the different types of problems for your final, but I just hope that this stuff kind of covered a lot of the stuff that kind of just makes everything work, makes the world go round here. Anyway, that's it. Have a good day. Good luck. Fiend.